In our previous video, we have examined the Arrhenius equation, and we have seen that the kinetic constant depends on different factors, one being the collision, not the number of collisions, the other one being the activation energy, can be thought as the energy barrier between reactants and products, and the other one is the temperature. Now, it brings a lot of chemical information to know the activation energy. So what kind of experiment or what kind of setup should we investigate so that we can calculate the activation energy? First of all, one needs to calculate the kinetic constant for different temperatures. So notice that our experiment should be set up. You need to calculate the kinetic constant for different temperatures, and you will find a table of kinetic constants and temperatures. Notice that to do that, one needs to again find the slope. For example, the logarithm for first order reaction, logarithm of concentrations over t, the slope gives you the negative k. So this would be one point of your table, and you perform the next experiment at a higher temperature or lower temperature and calculate a different constants. Okay, so now we have this table of constants and temperatures. We realize that as you increase the temperature, the kinetic constant increases. Fine, but how can we calculate the activation energy? Well, we have to manipulate the Arrhenius equation so that we can easily use all the factors. Because you could say, well, if I just have this and this, maybe I can just combine two equations and find this one. If you have an experiment, you want to use all of the points. So let's try to manipulate the Arrhenius equation so that you can find, as usually is the case in chemistry, a straight line, an equation that you can plot, get a least square fit. Notice that if you do the logarithms on both sides, logarithm of k is logarithm of a RT. I can separate this logarithm, so the logarithm of a product is the addition of logarithms, and the logarithm of an exponential is pretty much just the exponent. And I'm already doing it such that you can see that this is going to be my y, and this is going to be my x. So if I plot the logarithm of k versus the inverse of temperature, so one would need to build here in a spreadsheet, just calculate the logarithm of k and do the inverse of temperature and plot this y and x and do a regression, do a least square fit. The slope will be negative activation energy over r, and the y-intercept will be the logarithm of intercept, the natural logarithm of the prefactor a, the number of collisions. Again, we assume that a is constant through temperature, which is among small ranges of temperature is true. So here you have maybe a better graph. If you represent the logarithm of k versus the inverse of temperature, notice that the activation energy can only be positive, so the slope will always be negative. The slope will be negative activation energy divided by the gas constant. Therefore, now we know how to calculate the activation energy. Let's calculate, or let's try to solve a different set of problems. In this case, say that you're given the equation of a line. You have calculated different k's at different temperatures. You do the logarithm, you do the inverse, and you obtain this. Okay. Well, it's asking for calculate the rate constant of this reaction at this temperature. Notice that it's not asking for the activation energy. The activation energy would be given by this slope, okay, and this would be the prefactor. How can you calculate the kinetic constant? Well, in this case, we can just do this. The kinetic constant is a RT, okay, and how much is a? Well, if logarithm of a is 6218, a is a pretty large number, 62.18. Okay, so this will be 62.8. Oops, excuse me. Let's put the exponential. e to the 62.18 now times the exponent of, now this is negative 22,400. This is already my negative AR, and this is divided by the temperature. This will be in Kelvin this much. Okay, so this will give you the kinetic constant at this given temperature just by using the results that we got from the least square fit. Let's practice some more. In this case, actually, this is it's an old slide. It should say when the temperature increases from 298 Kelvin to 308 Kelvin. If you check your slides, this will be corrected. Anyhow, it's asking for what is the activation energy, knowing that the reaction rate doubles when you increase the temperature from 298 to 308. This is a typical case when you need to set up a system of equations. So for the 298 case, the rate constant is such that the activation energy divided by R, and this is at 298 Kelvin, and at 308 this has increased. A is the same, and this is at 308. Now we have to find the activation energy. Notice that we have no information regarding the pre-exponential factor. However, because we know that it's constant or approximately constant, we can do the ratio of these two equations. So if I divide the first equation by the second one, I get this: A R 298 A, and because we know, this is 308, and because we know that A is constant, this will cancel out. Now it says that the rate constant here of the reaction doubles. So when you increase the temperature, the rate constant doubles. So what relationship do we have? We know that if you multiply the one at lower temperature by 2, you have the second rate constant. So if you plug this in here, you will get that just as a factor of K1, and this will cancel out again. So it's going to be 1/2, and in here you will have, and again I'm just going to do it a little faster, R 298 times E. If it was dividing, I make it multiplying by changing the sign. Hopefully you're all comfortable with these kind of arrangements. Okay, and this is equal to E. I'm going to take factor from here, and this will be 1308 minus 1298. Okay, now the rest is just a little bit of math. I need to find the activation energy, so I take logarithms on both sides. Logarithm of 1/2 is equal to EA R 1308 divided by 298. I think I forgot. No, I'm good. Alright, so I'm just gonna follow here. Your activation energy is equal to logarithm of 1/2 times R divided by this ratio of temperatures. Okay, let me see. Okay, notice that this will give a negative number, but this will also be a negative number, so the activation energy will be positive. This equation, if you will, you can use this equation in here, or in general terms, let me put it this way: logarithm of K, logarithm of 2. This is an equation that you may use quite often. This would be AR, and the one that is negative is the one at T T1 over T2. Okay, you may want to use this equation in other contexts. This is what we have used. It's convenient because the exponential factor cancels out, and sometimes you're given a ratio between the rate constants at two different temperatures, and one can calculate the activation energy doing that.